Hi guys, so I've been getting some questions over 7.3 and 7.4, so I thought I would do a couple of exercises with you over these sections to give you some more supplemental material. So if you have questions, don't forget that there's a lot of resources available for you to get help. If you're in my online class, I can meet with you virtually. We can, during my office hours, there's online tutoring available. You can email me. There's the discussion boards, right? There's lots of options available to you. So please, take advantage of those. Reach out to me, and don't always wait till last minute to do homework assignments, because that can cause stress, and also you probably won't learn it as well if you're trying to rush through the material, right? All right, so without further ado, I'll go ahead and start this assignment. So this question is question number 2 from 7.3 homework, right? So we're told the letter T makes up an estimated 8% of a certain language. Assume that this is still correct, right? So if we're assuming that T gets 8% of a certain language, that's going to be my P, my population proportion, right? 0.08, right? And don't forget, in the population proportion, the P, this is my mean, right? So we're told to assume this is still correct. We're told a random sample of 1,000 letters, so 1,000 letters, is taken from a randomly selected large book, and all the T's are counted. So we want to find the approximate probability that the random sample of 1,000 letters will contain 7.1% or fewer T's, right? So I won't go through all the conditions, right? But there's enough information here for you to check all of the conditions for the central limit theorem. So we need a large sample, we need a large population, we need randomness, and we need independence, right? So I won't go through those details. I did those in the last video. So let's focus more on the calculation for this problem. So what I like to do is start with a picture. So the conditions are met. So the curve of this, we would expect it to look pretty normal, right? So that's why we can use the normal model. It's appropriate. Don't forget, with the normal model, the bell curve, the mean's in the center, right? So this would be 0.08 would be here in the center. And we want to find what happens if you get 7.1% or fewer T's, right? So if we look to the left of 0.08, right, somewhere here would be 0.071. So that's my p hat value, right? And then we need a shade to the left, right? And that's because it's 0.071 or fewer, right? So what I want to do is find this shaded area, right? And that shaded area is this, the probability that p hat is less than or equal to 0.071, right? So if I want to find the area of a normal model, I use normal CDF, right? So just like we've done at length in chapter 6, chapter 7, right? So we're going to go to second distribution, go to normal CDF, and then we need to type this in, right? So my lower limit is negative infinity, as it's already shown, right? Because I want this area from negative infinity all the way until we get to 0.071. So then my upper is 0.071. My mean is 0.08. And then my standard deviation, right? So in this context, we use the word standard error, right? So remember, to calculate standard error, we're going to take p times 1 minus p over n, take the square root of all that to find that, right? So p is 0.08 and n is 1,000, right? So you can actually just type in the whole calculation in this line. So we can just do the square root of 0.08 times 0.92, right? That's 1 minus 0.08, and then divided by 1,000, and go to paste, hit enter, and we get 0.147, right? So that's the solution, right? We're supposed to round to 3 decimal places. So we would have 0.147, right? So about 14.7%, right? So 0.147. 0.1. Right? So that would be your solution for this problem. So I think the easiest part to do is to draw this picture, right, and understand the shading part, right? That's why chapter 6 was so important in drawing the curves, right? And that's also why in concept check 6 I was having you draw the curves and find the probabilities, right? Because we're going to be using that a lot here on out, right? So it's really important to understand this concept, right? So don't forget, basically what's going on is, right, we're taking a bunch of p-hats, which are sample population proportions, and when we keep taking these, right, as long as the conditions are met, we expect them to follow normal, right? That's just what typically happens, right? If you study what proportions do, right? They tend to have this normal distribution, right? So that's exactly what we're doing up here, right? There's just a bunch of p-hats that form this normal model, right? All right, so hopefully that helps with that section. So I'm going to go to a problem I picked out for 7.4, which is on confidence intervals. So there's 4 parts to this. So we're told we have a simple random sample of 1,400 young men. 87% had earned a high school diploma, and we want to complete these parts, right? So again, in order to follow the central limit theorem, we'd have to check all the conditions. But let's assume that this is true, and we'll keep going through, right? So let me just pull up the PowerPoint from 7.4 just to remind you, right? So if starting on slide 7, it just talks about what is the margin of error, right? So remember, the margin of error tells us how far the population value, how far from the population value that our estimate can be, right? So what we would expect. If we go to this table, these are the values that we use for a certain confidence level, right? So, and this follows the central limit theorem, right? The empirical rule. So 95%, notice it says about to, right? Because remember, we used to do, 2 standard deviations with 95%, 1 standard deviation out was 68%, right, and so forth. So, but these are just more exact values, right? So you want to use these values from the table, and we're going to replace those in for z, right? And then the next slide were the equations to find the confidence interval, right? So we're going to take our point estimate, our sample population, and then add, subtract the margin of error, right? What we would assume that flux to be, this range, right? So we have to do some calculation here, right? And this equation is showing it with the margin of error, right? Because remember, to find the margin of error, we take that z-score from the table and then multiply it by our measurement of variation, which is standard error, right? And then here is standard error. So if we don't know what p is, we can plug in p hat to get what's called an estimate, a standard error estimate, right? So that's what this EST stands for, right? And one thing just to point out, the very last slide, right? The reason why this all makes sense. So, we have these confidence intervals getting wider as the confidence level increases, right? So this makes sense. If I want to be more certain that that my p is going to be within this range, if I keep making it wider, the more confident I'm going to get, right? So it's important to understand this idea, right? So the wider interval, the more likely you are, but also the less exact you're going to be, right? You're going to be certain that your number's in there, but your range might get pretty large, right? So you have to kind of find a balance for what makes sense. right, when you're doing this in practice. So with this problem, the first part is to actually find the standard error, right? And we're asked to round to 4 decimal places. So saying 87% had earned a high school diploma, this is the proportion from this sample of 1,400 people, right? So n equals 1,400, and this is going to be p hat, which is 8.87, right? 87%. So for part A, to find the standard error, we just need to plug in our equation, right? Standard error, the estimate, right, is equal to p hat times 1 minus p hat, all divided by n, and then the square root of all of that. Right, so we would have 0.87 times 0.13, right? That would be 1 minus 0.87, and then divided by 1,400, and then take the square root of all of that. So we could just plug this in our calculator. So square root of 0.87 times 0.13 divided by 1,400. Right, and I'm getting 0.00898 and so forth, right? But we're asked to round to 4 decimal places. So if we round this to 4 decimal places, we would get what? 0.0090, right? So then for part B, we're asked to find the margin of error using 95% confidence interval, right? So remember, the margin of error is by taking the z-score that we get from the table and multiplying it by the standard error, right? So if we go back to this PowerPoint, and this is also in the text, right? But we want this table. So to do 95%, right? We were doing 95%. We're going to use this z-score, 1.96, right? So this is more exact than using 2. Right, that's why before we said about 2. Right? So what we would do is take 2 times my standard error, and that will give me my margin of error. Right? So in other words, to find m, I wrote 2, but we don't want to use the approximation. Right? We want to use 1.96. I had 2 on my brain because I was telling you, trying to relate it to what we did before. Whoops. So 1.96. Come on. Doesn't like me making my dots. Right? So you would take 1.96 times the margin of error. Right? So what we would do is take 1.96 times 0.009. Right? So 0.009. And I'm using 0.009 since that's what we rounded to. Right? So typically when you have problems in my math lab that starts out with an answer and you round it and then you need to use that answer further down, you know, sometimes if you don't use the rounded answer to get the other answer, it might be a little off, it might be picky, so you might have to play around with that, right? So I'm just going to use this rounded answer, 0.009, multiply by 1.96. I get this value. Notice the unit here wants it to be a percent. So to turn this into a percent, I need to multiply by 100. Right, so now it's in percent form. We want to round to 1 decimal place. So that would be 1.8. Right, 1.8. Right. So then now to find the confidence interval, you're going to take, so to find the confidence interval, you're going to take your p hat and add and subtract the margin of error, right? Because this tells us how much it can fluctuate, right? So I would take my p hat, which is 0.87, subtract 1.8. Oops, excuse me. Since this 1.8 is in percent form, so should the p hat, right? So I'm going to do 87, right? So again, since this is in a percent form, I want to use this in percent form, which was 87, right? So take 87 minus 1.8, and then 87 plus 1.8. right? And that gives me my lower and upper bound, right? So it gives me 85.2 and 88.8, right? So then part D, if you're reading through this, this is suppose that in the past, 80% of all young people earned high school diplomas. Does the confidence interval you found in part C support or refute the claim that the percentage of young people who earn high school diplomas has increased? Right? So something to keep in mind is this confidence interval. What this means is that we're 95% confident that my p-value, right, my true population proportion that I don't know what it is going to be within this range, right? So basically, we used to be at 80%, but then now I'm 95% confident that my p is somewhere in between here, right? So if I'm really confident, 95% confidence, pretty darn confident, right? So if I'm really confident that p is within this range, then the whole range is above 80. So this would say that, yes, this seems to support the claim, right, that that I have increased the number of people that have their high school diploma, right? So this sample suggests that the population measurement changed, right, because it's unlikely that it didn't change, right? So for it to still be 80% and us to get a p-hat of 0.87, that's basically telling us, well, it's really unlikely to get a sample that's that big, so the population proportion must have changed, right? So what we'd be looking for, the correct solution here would be A. Right? All right, so I hope this was helpful. If you have questions, please take advantage. I'm happy to help. I really love statistics, and I really want to help you do well. Right?